Welcome back for the second part of this lecture. I often break a lecture up into smaller chunks just because you may not be able to sit for the whole thing, and it just makes it easier for uploading and downloading and all of that stuff. So we're going to continue talking about frequency distribution. You will remember that the frequency of each score or statistic or instance can be represented in a table or graphically. Sometimes we want to group the results into categories, and this is very much like assigning letter grades. When you all get A's in this class, your scores are going to fall between 90% and 100% of the grade in the class. So we group that together and we give it a value of A. We call that an A, and we give it a grade point value. Look at table 2.5 in your textbook. It is really a good one. Each group is called a class. So we've got a class or an interval that's called A, a class that's called B, class that's called C, and so on. On the grading scale, each of these class intervals is 10 percentage points. Let's use an example of a class interval from 40 to 44. In that class interval, all the scores are 40, 41, 42, 43, or 44. A score of 39 is in the previous class, and a score of 45 is in the next class interval. So 40 and 44 represent the score limits for the interval. A score of 42, just think of a score of 42, is somewhere actually between 41.5 and 42.5. Maybe it's 42.1 or 41.9, but we represent it as 42. So the exact value limits of 42 are really 41.5 and 42.5. We apply the same kind of reasoning to the exact limits for the interval. The exact limits for the interval that I've been talking about here are actually 39.5 and 44.5. Anything below 39.5 would be in the lower interval, and anything above 44.5 would be in the next higher interval. Why in the world does all this matter? It all seems awfully picky and fine-grained. If we say an interval is from 40 to 44, why does it even matter? The problem is that you will often be working with a mean or an average, and very often the numbers you will be using will not represent a whole number. The second reason has to do with some assumptions we make about class intervals. The first is that we assume all of the scores in that interval have the same frequency or are uniformly distributed. Going back to my example of a class interval between 40 and 44, if there are 10 scores in that interval, which I represented with a F equals 10, we make the assumption that there are 2 of each. It doesn't matter how many there were of each. We assume that they're evenly distributed across that range. And this is for mathematical reasons as we get on with using analysis. You see, as soon as we group the scores, they're not individuals anymore. They're spread evenly across the interval. And the second reason is that when we group the scores into an interval, we use the midpoint to represent all of them. So instead of there being 3 40s and no 41s and 1 43, instead we use the midpoint of 42 and we say that there were 10. The frequency is 10 at a midpoint of 42. This may seem like a lot of work. However, there are times when it is really necessary. want you to think that you want to know how parent income is related to acts of violence in school. Is there a relationship between the socioeconomic status and acts of violence? So, you sample 1,000 students from 3 high schools with a total sample size of 3,000. Now you need to look at their parent income. You really want to do an analysis with 3,000 different incomes, each of them slightly different than the other? It just doesn't make sense to go to that fine of grain size. It makes much more sense to group the incomes into intervals. So you're going to say all the students whose parents make between 0 and 36,000 a year, you're going to count those up. And in this made-up example, I'm going to say that I found 68 of the 3,000 kids their parents fell into that category. And then the next group is 37,000 to 72,000 per year. And I'm going to say that there were 512 students whose parents were in that category, and so on. And you see that this way, you end up with 6 categories to be doing your analysis with, rather than 3,000. You can see too why the exact limits are important. Let's pause a minute and think about this. If a student's parents make $98,432 per year, that is within the exact limits for the third group down. You can also see why the midpoint is used, as it's really hard to do calculations with a range. It's nearly impossible. So in this case, we would use the midpoint from each income bracket as we do our analysis. I want to point out just a few things about graphs that were discussed in the textbook. Remember that we usually use the x or horizontal axis for the independent variable, and the y is usually the dependent variable. Bar graphs. Remember that bar graphs are useful especially if the IV, the independent variable, remember that's going across the horizontal x-axis, is nominal or categorical. So things like gender, the make of the car, ethnicity, things like that. Those are good for bar graphs where we've got categories. Scatter plots. Scatter plots are useful when it's hard to distinguish between which is the IV and which is the DV. So we use scatter plots a lot in correlations and regressions. So things like comprehension and fluency. Which one is the IV and which is the DV if we're showing a relationship between them. Ability and semester hours of math. One doesn't lead to the other. The legal drinking age and drunk driving convictions. Things like that where we're trying to show relationships between them. Scatter plots are very useful for that. And finally, histograms or frequency polygons. Remember that we use those for frequency distribution. I want to talk to you a minute about cumulative frequency distributions. And we're going to come back to this, so if it doesn't quite make sense yet, let me know, but don't worry about it too much. Sometimes it's important to count for all the scores in one line so that you can see how many scores are above and below specific points. So we want to line them up. And this is called a cumulative frequency distribution. So if I have IQ scores for 34 students, I want to know how many students are above or below the 100 point. So I've got one student at 70, and that represents 4% of my sample. I've got 3 students at 80, and that represents 11% of my sample. And I've got 5 students at 90, and that represents 18% of my sample. And I've got 15 students at 100. So if I want to know how many students are below the 100 point, I've got 1 and 3 is 4, and 5 is 9. So I've got 4% of my students plus 11% of my students is 15, plus 18% of my students is 33. So 33% of my students are below that 100 mark in this sample. And to do this, once again, I need to consider that looking at the whole group, I always have that one student with 70%. That's 4% of my sample. And I have 11% of the sample at who have IQs of 80, and etc. And I could do this and account for all 100% of my sample. So 100 students who scored at 110, there were 8 of them, and that represents 7% of my sample. But look at the top blue line. As I add them together, by the time I get to the 2 students who scored 120, good for them, I've accounted for 100% of my sample. Now, how you'll see this used is when we line them up and we make a line graph that's called an ogive. It represents the percent of students at each increment of the IQ. So if you look at that 50% of my students, you can see how many fall below that and how many above. So we're going to come back to this when we look at percentiles.